Assalamualaikum warahmatullahi wabarakatuh, and hi again. Okay, this time around I'm going to give a lecture about chapter 6, multiple reactions. Before this, all this while you have been exposed about a single reaction. For example, like A plus B goes to C plus D. But in this particular chapter, we're going to deal with several types of multiple reaction, which is there will be one desired reaction. For example, this is desired reaction, and there are several undesired reaction, which can basically probably be like A goes to C, A goes to E, for example, and B maybe goes to F, for example, or maybe C, instead of becoming the product, it will also react with another component like B, and it will produce G, for example. So these are all the type of multiple reactions, including this, and this is the undesired reaction. So in this particular chapter, we're going to address how we're going to maximize the production, or in other words, in this particular chapter, we will deal more about selectivity. What is selectivity? How to improve the selectivity of the desired reaction. Here we will see that we will address the several learning outcome, which is after completing chapter 6, the student will be able to choose the appropriate reactor scheme to maximize the production of the desired product for any multiple reaction system, as well as to develop equations of concentration profile in any reactor for complex reaction. We will deal with 3 lectures, which is the first one on the type of multiple reactions, concept of yield and selectivity, maximizing the desired product in parallel reaction, which is by having one reactant only. In lecture 2, we will look into maximizing desired product in parallel reaction, but we have 2 reactants. And in lecture 3, we will look into maximizing desired product in series reaction, as well as developing algorithm for solution to complex reaction. There were several types of multiple reactions. Okay, as I said earlier, chemical reaction is usually accompanied by other side reaction, desired and undesired. The key factor for academic success is the minimization of undesired reaction through reactor selection. And there are 3 types of multiple reactions, which is parallel, series, as well as independent. Parallel means that one having the desired reaction and the second one is the undesired reaction. In terms of series reaction, the middle product is your desired reaction and this is your undesired reaction. And there also is independent reaction, where basically the first line may be the desired and the second line is undesired. Why yield and selectivity is important in multiple reactions? We would like to consider these particular reactions: A plus B to the desired product, and A plus B to the undesired product, with 2 different rate constant. In order for us to measure the instantaneous selectivity, it's basically just measure the rate of reaction of the desired divided by the rate of reaction of the undesired. The overall selectivity, however, is measured by the flow rate of the desired divided by the flow rate of the undesired. For the instantaneous yield, we are measuring the yield by measuring the rate of reaction of the desired divided by the reactant, the rate of reaction of the reactant A. For the overall yield, is basically measuring the desired flow rate divided by the amount of A reacted, the molar flow rate of the A reacted. So A is the key reactant. If you can imagine, if let's say we have a plug flow reactor, and let's say this is the section that we are measuring. If let's say the reactant goes in here and goes outside here, and we are measuring the RA here and RD here, this is how we measure the products, the instantaneous yield as well as instantaneous selectivity. This is also RU. But if let's say we start at the first reactor, entering reactor and exit of the reactor, so basically there will be FA here, there will be FD and FU here. So this is where we can measure the overall selectivity and overall yield. As exercise for you, you may want to try to write the overall selectivity and yield for batch reactor. Okay. In order for us to maximize the desired product for one reactant, hence we will maximize the selectivity. Basically, there are several key factors in order for us to change, in order for us to maximize the selectivity. The first key factor is the concentration as well as proper choice of reactor. So we consider the following reaction. A goes to D and A goes to U, and you have two rate constant KD and KU. If you write the rate loss, we will have the rate of reaction of the desired product equals to KD CA alpha 1, RU equals to KU CA alpha 2. The rate of disappearance of A is basically the sum of the rate of reaction of the desired as well as undesired. If you recall back, the selectivity, the instantaneous selectivity of SD to U is equals to rate of reaction of the desired divided by rate of reaction of undesired. And we replace with these terms to this particular place, we will get straight away equals to KD over KU C alpha 1 minus alpha 2. Okay, this is some exercise for you. You may want to deduce the selectivity formula for this particular reaction. Now we have 3 reactions in place. So have a thought about that and we'll discuss in the class. So what is highlighted here is that a ratio of alpha 1 and alpha 2 determines whether we need to keep CA high or low. So how are we going to do that? Imagine there are 2 cases right now. Okay, this is for one reactant. So there are 2 cases. One is alpha 1. Okay, recall back, RD over RU equals to KD over KU CA alpha 1 minus alpha 2. So now, imagine that alpha 1 is bigger than alpha 2, which means that this particular alpha is from the desired product. Alpha 1 is from the desired product. So, we know that if let's say alpha 1 bigger than alpha 2, we will have to keep high concentration of key reactant A. Okay, because this term will become positive, okay, S equals to RD, etc. So this term, if let's say alpha 1 minus alpha 2, so this, when we run at high concentration, everything will become positive and it will boost the rate of reaction of the desired product. So the first term, in order for us to maximize the selectivity, is by having high concentration of key reactant A. If let's say we are operating at gas phase, we should carry the reaction without the inert and it should be concentrated at high pressure. So what does it mean? But why don't we use inert? So can we think about that? If let's say we have liquid phase, we have to keep the use of inert to minimum. Again, this is addressing about inert, because if let's say we use inert, then basically we are diluting the concentration. Okay, so that is why we need to operate at high concentration. What type of reactor? So we have to use batch reactor or PFR, since in these two reactors the initial concentration of reactant is very high and it drops progressively through reaction. And we must not use CSTR, since in CSTR the reaction concentration drops to lower value immediately. So imagine here, if let's say we use PFR, there is a CA coming here, and then this is CAE. Along the length of this reactor, the concentration drop progressively. Okay, but if let's say we use CSTR, once it enters the CSTR, the concentration at this point is the same as the concentration at the outlet. So the concentration drops straight away, which is, those are the things that we don't want for the case alpha 1 bigger than alpha 2. For the second case, if now alpha 1 is less than alpha 2, so you know that if it is less, then the term here become negative. Okay, negative. And thus you know that in order for you, if let's say you operate at high concentration again, then you will promote more on the rate of reaction of undesired product. So what we have to do is keep low concentration of key reactant A and dilute the feed with inert or run reaction at low concentration of A. What we have to do is use CSTR, because the CSTR have the advantage of dropping the concentration straight away to the exit concentration. Or you can also use recycle reactor with product stream acting as feed diluent. Okay, so what we mean here is that if let's say we have a PFR, and then we can have a recycle loop, where we pass back the concentration of A to the inlet feed, and then the concentration is diluted. Does the temperature affect the multiple reactions? Yes, the temperature affect the multiple reactions. But how? Selectivity is also related to the activation energy. So, the temperature is the key factor number 2. Okay. Why is that? Because selectivity is related to activation energy through this. You know, just now we are dealing with concentration, alpha 1 and alpha 2. But in this case, KD and KU is also related to the activation energy, okay, as well as temperature. So, if the desired activation energy is bigger than the undesired, what does it mean? Is that RD increases rapidly with increasing temperature with respect to RU. Thus, the reaction should be carried out at highest temperature possible. So now try to imagine back, okay, the activation energy curve, right? Where basically this is one line, okay, and then so this is RD, and okay, this is RD activation energy line, and then there is another one, okay, sorry, and this is RU. So the activation energy, if let's say it is high in RD compared to RU, so you need high temperature for you to overcome the activation energy, the barrier. So that's why you need to operate at highest temperature possible. However, if let's say this is RU and this is RD, which means that now the activation energy for RD, for D, the desired product, is lower than the undesired product. It means that you don't need high temperature to overcome the activation energy, and therefore it should be carried out at lowest temperature possible, but not too low such that the desired reaction does not proceed to any significant effect. Okay, so these are the key terms in order for you to deal with single reactant. Okay, let us do some evaluation. Okay, reactant A decomposed by 3 simultaneous reactions to form 3 products, the desired product B and 2 undesired product X and Y. These gas phase reaction together with their corresponding rate laws are given below. How and under what condition, reactor type, pressure, temperature, etc. should the reaction be carried out to minimize the concentration of unwanted X and Y. So we have to evaluate first this kind of term. So what is the order of reaction for each? For example, A to X is 0 order, A to B is first order, and A to Y is second order. So you have to compare like alpha 1, is it bigger or smaller than the alpha D, which is this is the desired reaction, this is undesired 1 and this is undesired 2. So you have to check whether alpha D is it bigger or smaller than alpha U1 plus alpha U2. So if we check from here, it shows that alpha D is actually lesser than alpha U1 plus U2. Therefore, our strategy, we should refer to the case where it is alpha 1 less than alpha 2 case, where we have to operate by using CSTR, where we have to use very low concentration, we have to introduce inert, for example. So these are the case where how we deal with these three types of reaction. Now, we are also considering in terms of the K, okay, in order for us to decide on the temperature. So we have to compare again the activation energy. In this particular case, is what we have to do is comparing E1 and E2 plus E3 divided by 2. Okay, so is it smaller or is it bigger? If you calculate properly from here, it doesn't show anything. It is equals to 0. Okay, the difference equals to 0, which means that the temperature does not affect this particular reaction in order for you to maximize the selectivity. I think that's all for the lecture 1 for now, and I'm going to continue later on with the lecture 2. So just let's have some revision and try to understand what is the most important concept in this particular lecture. Thank you very much.